A bridge that could not move at all might actually be more likely to crack. That sounds wrong, because we usually connect strength with stillness, no shaking, no bending, no change. But a real bridge is constantly dealing with heat, cold, traffic, wind, vibration, and aging materials. In the sun, steel and concrete can expand slightly. At night, they cool and contract again. You may never notice it, but across a long bridge, tiny changes add up. If engineers tried to lock every part in place, the forces from expansion and contraction would have nowhere to go. Over time, the trapped stress could create cracks, distortion, or damage. A safe bridge is not frozen. It is allowed to move in the right places. Step back, and a bridge is not a stiff ruler laid across a river. It is a long structure that breathes with its environment. The deck, beams, piers, railings, pavement, and supports all experience small movement. Heavy trucks make it bend. Wind may make it sway slightly. Daily temperature changes can make the whole structure longer or shorter by a small but important amount. These movements are usually normal and expected. The job of engineering is not to pretend they do not exist. The job is to predict them, control them, and give them a path. Expansion joints and movable supports are part of that path. On the bridge deck, an expansion joint may look like a simple gap. You drive over it and hear a quick thump, or feel the tires bump for a moment. But that gap has an important job. When the bridge deck warms up and gets slightly longer, the joint can close a little. When the temperature drops and the deck contracts, the joint can open again. This movement is not a failure. It is a planned release. Wood floors, railway tracks, and building exteriors all have to deal with thermal expansion. Bridges do too, but on a much larger and heavier scale. The joint gathers unavoidable movement into a place that can be designed, inspected, and repaired. Look underneath a bridge, and another hidden part matters: the bearing. The bridge deck is not simply glued to the pier. Between the upper structure and the supports, bearings help transfer weight downward while allowing certain movements or rotations. Think of them like joints in a body. If your knee could not bend, every step would send force somewhere else. A bridge works in a similar way. When heat, cold, traffic, or vibration changes the shape of the deck, movable bearings let the structure slide, rotate, or adjust within a designed range. Different bridges use different systems, but the idea is the same: stability is not the absence of motion. It is motion kept under control. Inside a bridge, there is always a negotiation of forces. Vehicles add load from above. Sunlight can bring expansion. Cooling brings contraction. Piers and foundations carry forces into the ground. Expansion joints handle length changes. Bearings handle force transfer and movement. Drainage, waterproofing, and pavement all affect how long these parts can keep working. People sometimes assume every crack means poor construction, but materials naturally change with time, weather, and use. The real engineering challenge is control, inspection, and maintenance. If an expansion joint clogs, wears out, or stops moving properly, a small problem can create larger stress. A design that moves safely also needs care. At human scale, you may have felt this design without thinking about it. A car passes over a bridge joint and makes a thump. A scooter tire clicks over a seam. A pedestrian bridge may feel slightly springy under your feet. Those sensations are not automatically danger signs. Often, they are part of the structure working as intended. What matters is whether there are abnormal changes: a joint badly deformed, pavement lifting, loose metal pieces, poor drainage, or long-term water leakage. Ordinary people do not need to inspect bridges themselves, but the idea is useful. A bridge is not safer because it feels like stone. It is safer when tiny movements are guided into places built to handle them. Imagine two bridges. The first looks perfectly smooth, with no joints and no room to adjust. The second has visible gaps and support details that allow temperature movement. The first may look more complete, but when the day gets hot and the materials expand, the stress has to go somewhere. The second bridge looks less seamless, but those interruptions are planned safety spaces. This is where engineering often fights our intuition. A bridge that appears completely rigid is not necessarily safer. A bridge with joints is not necessarily weaker. Of course, gaps and bearings cannot be random. They must be calculated for the bridge type, span, material, temperature range, and expected use. The goal is not free movement. The goal is controlled freedom. So bridges may look motionless, but they expand and contract every day. Their strength does not come from pretending the world never changes. It comes from working with change. In the morning sun, a bridge may grow slightly. At night, it may shrink back. When traffic crosses, forces travel through bearings and piers. Expansion joints give the deck room to breathe. Most of these movements are too small for us to see, but they help large structures last. The next time you feel a bump on a bridge, it may be the space engineers left for movement. The dangerous bridge is not always the one that moves. Sometimes the bigger risk is a structure where every force has nowhere to go.